what I'm going to do is I'm going to have a video playing in the background. This will be in the first 5 minutes, and I'm just going to have this for you guys to understand intuitively while I give a quick background on what is going on. So right now in the repository that I showed earlier, we had 4 contracts, the most important of which is Vote Lottery. Vote Lottery will have 3 dependencies: ownable, safe math, and pairing. And with that group of 4, you're able to do the entire scope of this anonymous voting. At this point in time, what has happened is that voters are being added into an election. Let's say that there's an Alice, a Bob, and a Charlie who wish to vote for each other on who should become the new CEO of a decentralized organization. Alice, Bob, and Charlie know that they have other coworkers and there's other politics at play here. They want to vote for each other, but they also don't want to vote in a way that exposes any sort of hidden agenda. How would one conduct a fully anonymous voting process on-chain, right? Because if you consider anonymous voting in the Web 2.0 world, you are relying on the centralized database to have the votes be valid. If you have a decentralized organization, you would want to have a trustless way to have the same computations done in a distributed network. So this video is outlining the 3-step process. The first is the initial setup, where we deploy the contract and tell the election who are the candidates. In this case, that would be Alice, Bob, and Charlie. The second phase is the commit phase, where voters are able to register and they generate zero-knowledge keys offline. When those keys are saved, they're deployed and written to the blockchain, and a confirmation is sent. The third phase is the vote and claim phase. At that point, voters actually explicitly call the vote function using the same zero-knowledge keys that they generated offline, in addition to using the ticket that they used to register. When they registered, they get a ticket that is a single-time ticket for them to exercise their right to vote. After this 3-phase is done, what they will do is make the call to end the vote, and you can see in this video that the candidate Bob was the only one that received 2 votes. Bob is then the winner, and throughout the voting process, neither the identities of who voted or the identities of what each voter voted for was revealed. So this video is just simply in the repository, and I'm going to show you the code itself. So what we have right here is this is the set of 4 smart contracts. So in case you weren't around, I'm going to put this in Telegram. Might be hard to see, but it's there. And then I'm going to show you those 4 functions in Remix. This is just my Remix browser. If you guys are following along, please be sure that you are using the JavaScript VM provider, not Web3. I believe that would be MetaMask. So use the JavaScript VM, because for this demo, we have the zero-knowledge keys generated offline. So I'm going to go through the video explicitly. So we have Vote Lottery. This is this function that has all the methods that I talked about earlier. So let's just go over them one more time. We have add key, which this is the way that voters can register their key with the offline generated zero-knowledge proving function. Then you have add candidate. This is important to have in the setup process. This is for inputting Alice, Bob, Charlie, or you could put in as many candidates as possible, right? This could be a very large decentralized organization you have hundreds or thousands of people that can vote for. You have the transfer total Ether to winner. So when this contract was made, there's two use cases that you could use it for. You could use it where each person can use 1 Ether to vote, and in that case, the winner would have the most amount of votes and also the most amount of Ether, which means they would win the lottery. The lottery being also the result of the election. So it serves two functions. And vote. This is the method that that uses a pairing library that I'll go to in a second. But what this will do is ensure that the votes are done in the correct phase, the candidates are tallied up correctly, and we push the registered tickets out so that after they're used, they can't be used again. Let's quickly just look at candidates. I want to make the nuanced point that this is a private variable. So even though the functions are able to access this data, you're unable to use Web3 to get the real-time result of candidates. You're unable to write a public function to this smart contract revealing the contents of it as well. So candidates would be Alice, Bob, and Charlie. So I want to jump straight into the most complex part of the system. So this file is called pairing.sol. What it does is has, this would be the BN128 implementation of elliptic curve cryptography usable in Solidity. So to put it in short, elliptic curves are a way to allow the zero-knowledge system to work. So let's just go directly in. Right, this is the function call that ultimately gets called at the end of the day. This verifies a BN128 signature. That's the signature used to show that one knows the result in an elliptic curve of the form y squared equals x cubed plus b over a finite field. There's more you can read about that later, but elliptic curves are used in many different applications, ZK snarks, ZK starks, Reed-Solomon codes, erasure coding. All of these are important concepts, not just in privacy protocols, but they're very important concepts in allowing blockchains to scale in throughput and data consistency. So, how much time do we have? Okay. Cool. So we have 15 minutes. I'll try my best to get as far as I can on this live demo. And if we run out of time, I'll be sure to send the video links, and that has the full demo end to end.
10 minutes, actually. We do 5, switch over.
Okay, 10 minutes, that's fine. All right. Great. So we're back in Remix. Again, make sure that you have your account as the first account in JavaScript VM as the provider. Just hit deploy. You can see right here that it executed a new smart contract. Let me just pull this screen up. Yeah. So this deployed a new contract that's instance of Vault Lottery. And now we go to this deployed contract. What we're doing right now is, if you see this value field, this is how much Ether you want to deposit into as the starting payout for the lottery. In which case, let's just say 10 Ether. We hit the fallback function just to pay it out. We see that that just succeeded. We are now adding the candidates Alice, Bob, and Charlie. Make sure I spell that right. Let me just pull up my notes real quick. Okay, so in the repository, you'll see a file called ZKP keys. These are the keys that we were able to generate offline. This is not something you want to try at home. There's a library called Socrates. I believe that's the way to pronounce it. And Socrates is a Rust implementation of the BN128 elliptic curve. You're able to pre-generate these. This only has 2 potential voters. We're going to be using key 1 and key 2. If you want more, you would have to implement it yourself. But we are accepting pull requests. So currently we did step 0, and now we're at step 1. So let's just continue on like this. Okay. So right now what we're doing is we are going to be adding each of the keys in the elliptic curve. And I get to copy and paste this. So this transaction represents the fact that we successfully registered a ticket. We have add key. The address that submitted this now has the authorization to submit a hashed ticket. So now we do this for the second voter. Okay, so now the second voter is in. So now both voters have the ability to submit a ticket. So what is a ticket? So if you remember this key 0xCA35, going back to Remix, that's the first account. So everyone has the same starting accounts in the JavaScript VM. So everyone can also reuse these same key values. This 10 represents some sort of entropy. So 10 is just like the number you get at the DMV when you get a ticket. Because you want, in the DMV, it just counts up, but you want this to be as random as possible, and this cannot be on-chain. This is very important. It cannot be on-chain because even if you use the previous hash, you have a deterministic way of figuring out what exactly the next entropy value is, which makes it not, which defeats the purpose. This, in terms of UI, what some wallets do is that they'll force you to wiggle the mouse around a little bit and hash that bitmap or whatever, and then that turns into a number, and that's your entropy value. For something like this, we just let the users pick any arbitrary number. This hash right here is the result of inputting this random entropy value into a hashing function. For convenience, we are, for convenience, we want to look at the test hash. Something as simple as using the native keycache 256 is enough to just turn that number into a random hex string. Okay, so that's the result of add key, is that they can use those. So now we invoke start vote in the smart contract. Great. All right, so now, remember, I was on account 1 the whole time, and we're in a decentralized organization, so now we let any arbitrary user be a voter. And so that means we're going to skip to account 4. So using account 4, I am going to input these values in this function vote. what vote does is it takes a candidate, a hash ticket, and a 6-set tuple of the elliptic curves. So in this case, candidate, if you recall, we had Alice, Bob, and Charlie. So the candidate in position 1, if you're a software engineer, would be Bob. So when I input in 1, this means that I'm voting for Bob. And now I'm entering the rest of the elliptic curves. Sometimes this will actually just like fail because it costs too much gas. Okay, yeah, I'm going to mention this. Sometimes this call will actually fail arbitrarily because it will cost too much gas. This is something I believe will be fixed over time. Account 5. Now we are using account 5. So go back to over here, change it to account 5. Again, the first argument is candidate. Account 5 is also voting for Bob. So we keep 1 in that field. This hash ticket, if you recall, this was account 5 arbitrarily picked the number 30. So that means the hash of 30 is 0x588 something. Hit transact. Great. So now both registered voters have voted, and now going back to the owner, we can end vote. All right. So try to make this part bigger. So what you see here are the result of the logs, which show, I'll go into end vote right now. End vote calls get result, which calls emit. This is what logs the event. It emits the candidate name as well as the number of votes they received. So this is an array, as you see here. This would be Alice, the first item in the array. Now that the vote is over, it will emit the number of votes they receive, which is 0. This is Bob, the second or the first index value in the array. It shows that he has received 2 votes. And at the very end is Charlie, which you see received 0 votes. So there's still a few more cleanup functions that you have to do after this point. But in the interest of time, I'll let you guys do that yourself. What will end up happening is when they call end vote, they can now claim the reward, which means that if Bob was a person that entered himself into the vote, Bob can call claim, and the function will do a linear search on, remember, in elliptic curves, it's easy to verify, hard to prove. So he's able to verify just using a simple linear search that he's received all the votes, in which case he will be transferred the ether and or realize he's in the CEO position as well. So I hope that was useful, and I want to thank you guys all for coming. If you have any questions, I'll have my email on the screen. It's lmeng, L-M-E-N-G, @icash.io if you want to reach out. And again, we would be very excited to see you guys implement this in part of your hackathon project today.